Yes, it's Sam the guy. We are still continuing with our quinolones. Please don't forget to subscribe, like the video, and also share it. We are going to begin with chelation. Then we talk about the pKa and the mechanism of action. For chelation, these drugs, we know that they have that effect of the chelating with the cations, the prevalent cations. The chelation can be 1-to-1, can be 2-to-1, or 3-to-1. Drug with a metal ion, or 2 drugs with the 1 metal ion, or 3 drugs with 1 metal ion. So the likes of magnesium, aluminium, and iron is among others. Chelation can be like this, the 1-to-1, 1 drug with 1 cation. So we shall have resonance here. We have resonance between these 2 oxygens, the oxygen atoms. So we form a bond here and this bond. So we have this. You can have this chelation. This is 1-to-1. You may have 2 drugs with 1 metal ion. So it will be like this. The metal ion, then this one will form a bond. Also this one will form a bond. Then these bonds are represented as arrows. They are divalent bonds. We shall have this. Then in 3-to-1, we have 3 drugs with 1 metal ion. You have your iron. Then this oxygen will form a bond. Even this one will form a bond. This oxygen will also form a bond. Then these ones will just form like this as the arrows. So this is 3-to-1. Therefore, these drugs are contraindicated in case of oral formulation. They are contraindicated with milk. So they are not given with milk at the same time. If someone is taking milk, it's either 1 hour before taking that drug, or 2 hours after. So the person can take the drug, then 2 hours lapse, then he takes the milk. The drug is also contraindicated with hematinics. Also antacids. The mineral supplements shouldn't be mixed with the mineral supplements, because this will lead to chelation between the drug and the metal ion, leading to decreased absorption of the drug and the ion. So both the drug and the ion will not be absorbed easily. This can increase the effect, the anxiety effects, the nausea, because the drug will remain in the anxiety, vomiting, among others, the anxiety side effects. Now, this is the chelation. Let's talk about the pKa. When it comes to pKa, we have 2 main groups which participate in this. The carboxyl group, which is acidic, weakly acidic, and this nitrogen, the amino group here, which is basic, weakly basic. In the basic media, this group will ionize, releasing the hydrogen ion into the medium. So it will be like this, to be minus. So the hydrogen ion will be released into the medium. But in acidic media, this nitrogen here will attract the proton. So it will be plus to ionize like this. So we can have the zeta ion. When these two groups are both ionized. Here the pKa is 5.1. I mean it is 5.6 to 6.4 pKa for this. Then pKa for this one is 8.1 to 9.3. So when you look at this, meaning this part, though it is acid, but it is very, very weak. It is very, very weak. Because when you compare it to the benzoic acid, which is around 4.2, this one is more acidic than this part. Why? This is because of the hydrogen bonding here. This hydrogen tends to form a bond with the oxygen here, this ketone group, reducing the ability of this hydrogen, the proton, to be released into the medium. Therefore, reducing the acidity of this group. But here, we are seeing that the pKa is high, of course, meaning that this one is highly basic. This one is acidic, but it is weakly, it's more weakly acidic. What's the effect of this? This group may lead to poor ionization. The poor ionization, if it is poorly ionized, will lead to accumulation of the free drug in the medium, leading to crystallization. In case the media is basic but not too basic, this one will lead to poor ionization because of the hydrogen bonding. But this group can ionize in case if the pH is below this range, it will ionize. This one will ionize if the pH is above this, for it to ionize. But at isoelectric point, these two groups, they will have the same charges. They will both ionize, and at isoelectric point, meaning that there is equal positive and negative ions. This reduces the interaction with water molecule, so leading to reduced solubility. This is one of the reasons why at very high concentration, also when there is reduced hydration. Of course, if the hydration is reduced, the concentration will also increase. And increase in the basic pH, or increase in pH, of course. If it is basic, meaning it is high, increase in pH leads to, it can lead to crystalluria. In case of in the urine, that's why there is a risk for high concentration of the ciprofloxacin in case there is dehydration, and if it is concentrated much in the urine, because the isoelectric point of the ciprofloxacin is around 7.4, and assume if the urine pH is also around 7.4, meaning that both of the acidic and the basic region will both be ionized. When they are ionized, leading to reduced solubility of the drug. And also, because of this, and there is dehydration, increased pH, we can have the crystalluria. Why do these drugs not crystallized in the blood or in our system? One, they are given in low concentration. The concentration given doesn't allow the precipitation of this drug in the system. They are given in low concentration. Another thing, at isoelectric point, the pH or the solubility is not totally zero. It's not totally zero, of course. The pH is not total. The solubility is not totally zero. Those are some of the things we can talk about the pKa. This group ionizes if the pH is below this, and this one ionizes if the pH is above this. But you can have the isoelectric point for these two at around 7.4, depends on the drug. But in case of the ciprofloxacin, it's around 7.4. So in pH of 7.4, this drug can have the risk of the crystallization, but it may not happen because of the concentration given is lower. Doesn't allow this to happen. But in urine, because of the increased concentration of the drug, and in case of the dehydration, we can have the crystalluria. This is just an example, but many other drugs, the floroquinolones, can have the same effect. When it comes to the mechanism of action,